Hello everyone, and welcome to the Waveshare ESP32 Arduino Getting Started tutorial. In this lesson, we will learn one of the most fundamental and commonly used communication methods, UART serial communication. It is the basis for outputting debug information to a computer, and it is also widely used for communicating with various peripherals, such as GPS modules, fingerprint recognition modules, and more. Let's get started. UART stands for Universal Asynchronous Receiver Transmitter. It is a hardware interface used for asynchronous serial communication. To implement UART communication, two core signal lines are needed. TX, used to send data. RX, used to receive data. When wiring, you must connect the transmitting end TX of device A to the receiving end RX of device B. Similarly, the receiving end RX of device A must be connected to the transmitting end TX of device B. At the same time, the ground lines G and D of both devices must be connected to achieve what we often call a common ground. This provides a unified voltage reference level for both sides and is key to ensuring proper communication. This connection method enables full duplex communication, meaning devices can send and receive simultaneously without interfering with each other. Another main feature of UART is that it is asynchronous. This means that, unlike synchronous protocols such as I2C and SPI, the communicating parties do not need to share an extra clock signal line to keep their clocks synchronized. Therefore, to correctly send and receive data, both sides must agree on the same parameters in advance, such as the transmission speed and the data frame format. The baud rate defines the speed of UART communication, measured in bits per second. When the baud rates match, the receiver can sample the signal line at the correct moments to accurately decode zeros and ones. The common baud rates are 9600, 115-200, etc. The data frame format specifies the structure of each data packet. Each data frame starts with a fixed start bit. This is followed by the actual data bits, typically 8 bits. Then there may be an optional parity bit for error detection. Finally, the frame ends with 1 or 2 stop bits, marking the completion of the transmission. Only when the baud rate and data frame format of both parties match exactly will UART communication succeed. The ESP32 chip typically integrates 2 or more independent UART controllers. Each UART controller can independently configure parameters such as baud rate, data bits, stop bits, and parity. In the Arduino environment, we can use these UARTs via objects like serial, serial 1, etc. Serial is the default serial port. It is usually connected to the USB to serial chip on the development board. We use it to upload code and print information to the serial monitor. For ESP32 models with native USB support, serial can also be used for this purpose. Serial 1 is an additional hardware serial port. We can assign it to almost any free GPIO pin to connect other serial devices. A major advantage of this design is that we can use serial to connect to a computer for real-time debugging while simultaneously using serial 1 for stable, independent communication with external hardware modules. The two do not interfere with each other. Besides serial and serial 1, many ESP32 chips, such as the ESP32S3, provide even more UARTs, like serial 2. For the exact number of available serial ports, please refer to the datasheet of the chip model you are using. Now that we've covered the theory, let's start with our first hands-on example. This example will demonstrate how to send commands from the computer's serial monitor to control an LED connected to the ESP32 development board. Before programming, let's build an LED circuit. Components needed: 1 ESP32 development board, 1 breadboard, 1 LED, 1 330 ohm resistor, a few jumper wires. Please follow the wiring diagram on the screen. Now let's look at the code. First, we define the pin variable. Then, in the setup function, we use pin mode to set the LED pin as output. The core line is serial.begin 115-200. which starts the default serial port and sets the baud rate to 115-200. The baud rate set in the serial monitor must match this. In the loop function, first we use serial.available to check if there is any data in the serial receive buffer. If there is, we use serial.readStringUntil to read a string until a new line character is encountered. Then we use msg.trim to remove any whitespace characters from the beginning and end of the string. When we type text in the serial monitor and press enter, besides the typed text, a carriage return and new line are usually appended. The trim function helps us clean up these extra characters, ensuring that the subsequent string comparison like msg=on works correctly. Finally, we use an if else if statement to check whether the received string is on or off. Execute the corresponding digital write operation to control the LED, and send an operation feedback message to the serial monitor via serial.println. Alright, let's upload the code. After uploading, open the serial monitor. Don't forget to set the baud rate in the lower right corner to 1152,000, matching the code. Now type on and press enter. You will see the LED turn on. Type off and press enter. The LED turns off. Next, let's look at a more advanced example, how to make two ESP32 boards communicate via UART. We will use a button connected to board A to control an LED connected to board B. This time, we need two sets of components, two ESP32 development boards, two breadboards, one LED, one 330 ohm resistor, one button, several jumper wires. Board A builds a button circuit, reading the button input connected to GPIO pin 7. Board B builds an LED circuit using GPIO pin 7 to control the LED. Wiring between the two boards. GPIO 12 of board A connects to GPIO 1 of board B. GPIO 11 of board A connects to GPIO 2 of board B. Also note that the GND pins of both boards must be connected together to achieve a common ground, otherwise communication will fail. Let's examine the code. This time we have two pieces of code, one for the sender and one for the receiver. Both pieces of code initialize serial for debug output to the computer, and also initialize serial1 for interboard communication. Focus on the serial1.begin function. The first parameter, 9600, is the baud rate. The baud rates of the two communicating parties must match exactly. The second parameter, serial8n1, is the data frame format. 8 data bits, no parity, 1 stop bit. Both sides must also match this. The third and fourth parameters, UART1RX pin and UART1TX pin, are the GPIO pins we assign to serial1 for RX and TX. Now look at the correspondence between wiring and code. The transmit pin TX of sender A connects to the receive pin RX of receiver B. The receive pin RX of sender A connects to the transmit pin TX of receiver B. The logic on the sender side. Set the button pin as input with internal pull-up. This makes it high when not pressed and low when pressed. Detect changes in the button state. When the button is pressed, send the character 1 via serial1.write. When released, send the character 0. The logic on the receiver side is simpler. Continuously check serial1.available to see if data has been received on serial 1. Once data is received, read one character with serial1.read. If the character read is 1, turn the LED on. If it is 0, turn the LED off. Upload the two pieces of code to their respective development boards. Now, when we press the button on the sender board, the signal travels through the serial lines, and the LED on the receiver board lights up immediately. Release the button, and the LED turns off. You can also open two Arduino IDE windows, open the serial monitor for each board, and view the debug information being sent and received on both sides in real time. This demonstrates how to use an extra serial port on the ESP32 to achieve UART communication between devices. Alright, that's all for this lesson. Let's quickly recap. We learned the core principles of UART serial communication, including TX or RX cross-connection, common ground, asynchronous communication, and the importance of baud rate and data frame format. We practiced interacting with the ESP32 via the computer's serial monitor. We also implemented UART communication between two ESP32 development boards. In the next lesson, we will learn another commonly used communication protocol, I2C. Thank you for watching. If you found this video helpful, please like this video and subscribe to our channel. See you in the next lesson.